Hi, my name is Samer Saab, and this is a quick 3-minute video on our work on adaptive heavy ball method. First-order gradient descent methods have gained wide popularity in machine learning as they are well suited for large-scale systems due to their cheap computational costs while achieving high performance. Despite their success, however, they face two major limitations. The first limitation is the amount of time spent on tuning an optimizer. There exists a combination of hyperparameter values that will yield the best performance according to some user-defined metric, and finding this combination of values can be burdensome, as the most common approach is a greedy search where many different values and combinations of these hyperparameters are tried together until the desired performance is achieved. The second limitation is convergence, whether it is guaranteed and under what assumptions. For example, the Adam optimizer was found to be divergent even in the convex. And so I present to you the heavy ball method given by the equation over here, which is a popular first-order gradient descent method and was found to achieve the fastest local convergence rate provided that the function is mu strongly convex and L smooth. In fact, Polyak was able to work out the optimal hyperparameters that would achieve such convergence rate. But the problem with these hyperparameters is that they require the knowledge of the Lipschitz constant L and the strong convexity measure mu. And in functions as complex as deep neural networks, it is not feasible to assume that you have this knowledge beforehand. Therefore, in this work, our objective is to devise a self-adaptive heavy ball method that iteratively approximates the Polyak hyperparameters, that achieves global convergence in the deterministic setting, that has performance comparable to popular optimizers when implemented on neural networks, that has no substantial addition to computational complexity while requiring minimal to no tuning. And so for tractability of analysis, we'll begin by assuming that our cost function can be approximated by a quadratic cost function at each xk, as shown in the image to the right. Using the following notation, we can go ahead and create our approximation algorithms of our local Lipschitz constant Lk and of our local strong convexity measure μk. Using these two, we can go ahead and approximate and adopt the Polyak optimal hyperparameters. We were able to show that our adaptive heavy ball method can achieve global linear convergence rate to the solution in the deterministic setting given that the cost function f of x is mu strongly convex and L smooth with a sufficiently large gamma greater than or equal to 1. We empirically validated our method on 4 different experiments. Keeping in mind that we'd like to reduce the amount of time spent tuning, we only tune our method on the first 3 experiments which had very cheap computational costs, and the 4th experiment we do not tune our method at all as it was used on a deep neural network. On the Lissard problem, our adaptive heavy ball method was shown to outperform the optimal heavy ball method in both noisy and noiseless cases. For positive semi-definite quadratic functions, our heavy ball method was able to outperform a time-varying and time-invariant heavy ball method. It was able to outperform 6 other popular first-order gradient descent optimizers on the non-convex BL function. And lastly, it was very comparable to 5 well-tuned popular first-order gradient descent optimizers on the image classification tasks using deep neural networks. Thank you.